Hello there, everybody. What's going on? My hair's a little sweaty. That actually gave a little away. Whoops. But welcome back to Discrete Math. I'm so happy to have all of you. How am I doing? I'm doing all right. Thanks for asking. Actually, weird thing in my life, you might have noticed that no one else is here actually talking to me. It's just me, which is, of course, what this is always like when you guys leave the Zoom lectures and me talking to myself in this room forever. I only exist in this space. But beyond that, it's because someone forgot to press the record button at the beginning of the lecture today. So during the live recording, well, I can't call it live recording because nothing actually recorded. The point is, I get to give this entire lecture again, which luckily I love math. So it's okay, I just love it so much. But anyway, so let's get to it and get to learning some discrete math. Today, we are finishing up our discussion on strong induction, or at least I hope we're finishing up. That's why I said a few hours ago, and we're finished. But anyway, so today we're talking about strong induction again. Let me get this straight going here. I'm trying to avoid this glare. I will figure this out. I have special lenses coming. But anyway, yes, we're talking about strong induction. And if I had the energy, I would write strong mathematical induction, but I think you guys know what's going on. This is strong induction. Let's just go over the idea of strong induction again. So before we get into it, just real quick. So the idea of strong induction is whenever proving a claim that goes like this. So you claim, so I'll say to prove that for all n and a set x and n such that x is greater than or equal to some a. So this is your set. This is just saying that x is a natural. This is a set of all natural numbers bigger than or equal to a. So everything a and above, right? So to prove that for all n in this set p of n by strong induction, it goes like this. So first you have a proof, and then you say proof by strong induction on n or whatever, and then you have your base cases right here, and your base cases, these are the oh, the lines are back. The lines are back. This is interesting. So you guys might notice some very faint lines coming to the screen. That's because the light is an LED. I think we talked about this last time. But anyway, I figured out how to fix it. It's just turn the light on and off, and it goes away. So anyway, so base cases, remember, when you're trying to prove these things, are your kind of beginning foundation of this domino chain reaction effect kind of thing. The way I like to think about it, well, actually, let me write it down first. So in the base cases, you'll prove that the first few of these are true. So you'll just straight up verify that PA is true, because it's everything above A, so you start with PA. So this will always be in a base case. And in weak induction, you'd stop there. There's only one base case. But in strong induction, there might be multiple base cases because it might end up requiring our inductive step, where we say that, oh, okay, if this claim works for everything up to n, it'll work for n plus 1. You'll see that in a second. Our inductive step to work might require a few previous cases, so we need some base cases backlogged to use in that first inductive step, and then that'll get us to the second one, the third one, or the fourth one, or the fifth one, the sixth one, go on and on and on and on and on. So anyway, so we'll prove P of A is true, and then we'll prove that like P of A plus 1 is true. And then you keep going, and eventually your last base case will be P of B is true. So P of B, so B is a number bigger than A, and it's the last thing that will prove, it's the last number will prove is true, follows P with the base case. So that's when we're to verify. Everything else, we're going to use the previous steps via the inductive step. So then after the base cases, you have, of course, the inductive step. And here, the inductive step, here's the part where you want to show that for all n greater than or equal to b, it's going to be your last base case. These are going to overlap. For all greater than or equal to b, P of A and P of A plus 1 all the way out to and P of B, or sorry, not P of B, P of N will imply P of N plus 1. So the whole idea here, right, is that the inductive step, you want to show that if everything up to N is true, then P of N plus 1 must also be true. That must also follow. And I really like to think about this as we've all been there, right? We were trying to like crank your old-timey 1920s car, and you got to get in front of it. You got to put the thing in, you got to crank it, right? The base cases are like your first few cranks when you do that. And eventually, after you crank the old-timey car, the engine will take over and that chain reaction starts. And that's what the inductive step is. So your base cases are the first few cranks to get you over the hump, to get you to the inductive step. And so the question, I guess, a lot of the times is, well, how do you know how many base cases you need? And it all comes down to how many previous steps you need to use in the inductive step. So I'll write that right here. So I'll say number of base cases needed is determined by how many previous cases the inductive step needs to prove the next step. And so we can see, actually, this is why in weak induction, we only have one base case. Because in weak induction, right, so instead of saying that all of these, before the weak induction had, like, we don't assume that everything up to N is true. We just assume that P of N is true and then show P of N plus 1. So in that case, we only need P of N to prove P of N plus 1. So the inductive step just needs one previous case, P of N, to prove the next case, P of N plus 1. So that's why we only need one base case. But there are plenty of proofs that we can think of, and we're going to do today, where the inductive step actually requires at least a couple, if not more, of the base cases, or sorry, at least a couple of the previous cases to prove the next case will hold. And so then you need a few of those base cases, your foundation, your first few cranks, and then the inductive step will take over. This will all make more sense with an example, but this is the idea. Prove your base cases, prove that everything up to N is true, then N plus 1 is true. That means then, well, then N plus 1 will be true because N plus 1 is bigger than N. First of all, that would prove B is true because this works for all N greater than or equal to B, and B is certainly greater than or equal to B. And so you can use this to prove that everything up to B is true. Well, then P of B plus 1 will be true. But we know everything up to B is true because of the base cases. So then you know everything up to B plus 1 is true, but B plus 1 is greater than or equal to N. So if this is in fact true, then you can use everything up to B plus 1 to prove that P of B plus 2 is true. This goes on and on and on and on and on. I feel like I am a broken record. So I'm just gonna move on. There we go. I'm just gonna move on broken records like all hipsters should. Let's actually do the proof from last time. I have it written right here. So the proof from last time, or finish up the proof we were talking about last time, goes like this. So first of all, let's define this sequence H. DF's defined. The sequence goes like this. We define H of 0 to be 1, H of 1 to be 2, H of 2 to be 3, and then we define H of K to equal H of K minus 1 plus H of K minus 2 plus H of K minus 3 for all K bigger than or equal to 3. So for H of 0, H of 1, H of 2, there's just initial conditions. They're just defined. But for all K bigger than or equal to 3, once the index is bigger than or equal to 3, we can discover what the sequence is based on this recursive formula. So this is a recursively defined sequence right here. And notice, right, recursion and induction both have this like self-generating nature to them where you plug in a few initial conditions or base cases, and then there's some general step that can get you from previous cases to the next step, and you can keep generating from there. Keep feeding it back into itself. So this is like what the idea of recursion is. And so it's going to make a lot of sense that we're going to end up using an induction proof to prove something about this recursive sequence, because induction proofs are inherently recursive and the sequence is inherently recursive. But anyway, let's just refresh ourselves on what this is, just to give a practice. So to calculate h of 3, for example, using this recursive formula, what you do is h of k minus 1 plus h of k minus 2 plus h of k minus 3. This is just the sum of the 3 previous terms, right? Like if this is h of k, the one before it's h of k minus 1, the one 2 before it's h of k minus 2, on and on. So h of 3 will be the sum of the 3 previous terms. So that would be h of 2 plus h of 1 plus h of 0, which in our case, h of 2 is 3, h of 1 is 2, h of 0 is 1, 3 plus 2 plus 1 is 6. So that is, that's what h of 3 is. And then we do the same thing, we calculate h of 4, h of 5, on and on and on, out to infinity. Anyway, so why do we care about this sequence? Well, there's a very interesting claim we can make about it. And the claim goes like this. Claim. For all n in x in z such that x is greater than or equal to 0. So for all n in this set right here, by the way, when I was talking about the idea of strong induction earlier, I might have accidentally had an n here instead of z. It should be a z, because z includes negative numbers, and there's no reason why you know, you don't say it's true for everything bigger than or equal to -5. It's totally fine to use negative numbers. But anyway, the claim is for all n greater than or equal to 0, we have that h of n is less than or equal to 3 of n, 3 to the n. That's totally our claim. And now let's just do an aside and talk about why we would think this is even true. I mean, we could try it out for a few examples, right? I mean, we can look at h of 0, and yeah, h of 0 equals 1, and 3 to the 0 equals 1. So 1 is less than or equal to 1. H of 1 equals 2, 3 to the 1, right? 3 to that index is 3, and 2 is less than or equal to 3. So we can do more and more of these, and we see it keeps working out. But the question is, how can we prove beyond any doubt that it will always work out? That we'll never, ever, ever be in a situation where it's not true? That's a trickier question, right? That's a very tricky question. But luckily, we have a very tricky solution, and that is strong induction. So here's the idea. I'll write it down. If we can prove that whenever the 3 previous cases hold or are true, the next case will be true. We're done. So by strong induction, if we can prove that whenever the 3 previous cases follow this claim, right, follow the claim that h of n is equal to 3 at the end, follow this idea. Sorry, choking on almonds again. No, anyway, if we can prove that whenever the 3 previous cases satisfy the claim, that the next case will satisfy the claim, well, then we'll be golden, because these 3 cases satisfy the claim, right? We already showed h of 0 is less than 3 to the 0, h of 1 is less than 3 to the 1, h of 2 is less than 3 to the 2. That all works. And if we can show this, that whenever the 3 previous cases are true, the next case will be true, well, then what we're showing is that, well, it's like these 3 cases are true, so the next case, h of 4, should be true. And in the next case, h of 5, since we show that h of 4, h of 3, h of 2 are true, will be true. In this case, h of 6, h of 5, h of 4, h of 3 are true, will be true. This is the chain reaction. This is the old-timey car crank that keeps things moving forever, proving that this claim is true for all n, greater than or equal to 0 at least. So that is the idea. So what we really want to show So we want to show that for all, so we eventually want to show that claim is true for n plus 1, assuming claim is true for n minus 1 and n minus 2, because those are the 3 previous cases. I hope this is making sense. So the idea is, once again, to prove the next case just from the truth of the previous cases. And if we can do that and we have the base cases, strong induction will take over this chain reaction. So if we want to show the claim is true for h of n plus 1, that means we really want to show that h of n plus 1 is less than 3 to the n plus 1. That's what it would mean if the claim is true. So let's check it out. So notice that h of n plus 1, well, what's that equal? Can we write that in terms of the previous cases? Because that'll really be helpful. And it equals h, so the 3 previous cases from n plus 1 are going to be n plus n minus 1 plus h of n minus 2, like I said there. So that's what h of n plus 1 is. It equals that. And so I kind of said this backwards. I wish this the other way around. Whatever. The point is that from this we can see why we care about the 3 previous cases. Because maybe if we can show the claim is true for all of these, then we'll be able to somehow in a roundabout way be able to show the claim is true for this guy. So anyway, assuming the claim is true, so if claim true for n minus 1, n minus 2, then we'd get that h of n is less than or equal to 3 to the n. H of n minus 1 is less than or equal to 3 to the n minus 1. And h of n minus 2 less than or equal to 3 to the n minus 2. That's just what it means for the claim to be satisfied for these 3 h's. And so in our formula here, since h of n plus 1 equals h of n plus h of n minus 1 plus h of n minus 2, it's certainly going to be less than or equal to, going off the screen a little bit. It's certainly going to be less than or equal to 3 to the n plus 3 to the n minus 1 plus 3 to the n minus 2, right? We just replace everything here with something that's bigger. But we eventually want to somehow get this to be less than or equal to 3 to the n plus 1. That's what we want to do, right? We want to show that that h to the n plus 1 is less than or equal to 3 to the n plus 1. This is the time in class where I took a long pause and asked if anybody had any suggestions. If you have them, yell at the screen right now. The point is, we have to figure out some way to relate these 3 guys to this. We really want to show it's smaller. Here's the thing to notice. The thing to notice is that I'll say notes. Three to the n plus 1, right, equals 3 to the n times 3 to the 1. That's just an exponent rule. And then 3 to the n to 3 to the 1, well, I'm just going to change the order here. That's just 3 times 3 to the n. And what's 3 times 3 to the n mean? If we don't overthink it, it's 3 to the n added to itself 3 times. So this is just 3 to the n plus 3 to the n plus 2 to the n. Now we're cooking. These two look really similar, right? They're both an addition of 3 powers of n. Just this one has the powers being n minus 1, n minus 2. This one has n, and n. But what's the thing you notice? The powers here are always bigger. They're always bigger. And note that 3 raised to a bigger number is bigger, right? 3 raised to n is bigger than 3 raised to the n minus 1. 3 raised to n is certainly bigger than 3 raised to the n minus 2, because 3 to the n minus 2, 3 to the n is 3 to the n minus 2, and 2 more additional powers of 3 above that, right? So the point is that I'm gonna avoid this glare. I'm gonna go under it. Ooh, I saw that coming. The point is that now we can say that this is less than or equal. 3 to the n is less than or equal to 3 to the n. 3 to the n minus 1, that's again less than or equal to 3 to the n, because 3 to the n is a bigger power of n, or bigger power of 3. 3 minus 2 again is less than or equal to 3 to the n, because 3 to the n minus 2 is a smaller power than 3 to the n. But then we can do this exact math that we just did. 3 to the n plus 3 to the n plus 3 to the n, that is 3 times 3 to the n, and that just equals 3 to the n plus 1. So if we follow this out, we see that if we assume the claim is true for the 3 previous cases, then we can prove the claim will be true for the next case. If h of k is equal to 3 to the k for the 3 previous things before n plus 1, and then the h of n plus 1 must be less than or equal to 3 to the n plus 1. It just has to happen. And this is exactly what we want to prove, or we want to show. This is the thing we needed to show to really do proof by strong mathematical induction, right? Because basically what this shows is that if the claim is true for everything up to n, then it'll be true for n plus 1. And that's all we need to show. Once you get the base cases all sorted out, then this self just keep feeding this back into itself, and it keeps proving us more and more and more and more cases for free. So, any questions? Sadly, you can't ask me. But anyway, I'd pause it if you needed to see that more, or think more. Feel free to email me if you have any questions on these kind of things. Let's go down to business actually trying to prove this. So, still proof. And the proof is by strong mathematical induction on it. And so we always start with the base cases. But there's a very interesting question of how many base cases we needed, right? And we said earlier, right, when we were talking about strong induction, I say right a lot when I have no one to bounce ideas off of. We said earlier that the number of base cases you need depends entirely on how many previous cases you need to be true in your argument. And so let's think about this. So our whole idea, right, was that h of n plus 1 equals h of n plus h of n minus 1 plus h of n minus 2. And we can eventually show through a chain of these less than or equal that that's less than or equal to 3 to the n plus 1. That's kind of what we did on this side. But that's not always true. Right? I kind of hid a thing in here, right? This is not always true. This isn't true for h of 0, for example. H of 0 isn't equal to h of negative 1 plus h of negative 2 plus h of negative 3. This recursive formula only applies when k is equal to 3, when the index is bigger than or equal to 3. But we need to use this recursive formula to do our proof h of n plus 1 is actually less than or equal to 3 to the n plus 1. So in order for this inductive step to take over, in order for our argument to work, we need n plus 1 be greater than or equal to 3. So we want this index to be greater than or equal to 3. But then subtracting 1 from both sides, that means we need n to be bigger than or equal to 2. So this works as long as n is bigger than or equal to 2, right? That is when the inductive step kind of starts taking over. And so what that means is that everything up to 2, we need to verify with base cases. Because even though, like I said, it starts at 2, what that means is we can use everything up to 2 to prove that it's true for 3, to prove that P of 3 is true. And so that means the first thing we can actually prove using induction, the inductive step in the previous cases, is 3. That's true for 3. And so we need to prove everything up to 2 manually. But after that, this whole argument just takes over automatically and proves everything. So let's get going. Oh, it's a beautiful voice sometimes when I'm alone at night. So base cases. So what I just said is that we need to prove everything up to 2. And so let's go ahead and say let n equal 1. We need to prove the claim is true for 1. What's the claim again? It's that h of n will be less than or equal to 3 at the end. IKA, in this case, we want to show h of 1 is less than or equal to 3 of the 1, which we already did. Actually, no, I'm sorry. We don't want to start at 1. We want to start at 0, right? Because, right, our set starts at 0. We're trying to prove if everything equal to 0. Let's go ahead and let n equal to, let n equal to 0. Note h of 0 equals 1 by definition. Further, 3 to the 0 equals 1. Thus, h of 0 is less than or equal to 3 to the 0. Done. That easy. Right? Now, that's for 0. Let's do 1. So 1, again, we're trying to prove that h of 1 is equal to 3 to the 1, trying to show the base the claim holds for 1. So let's go ahead and note that h of 1 equals 2. And further, 3 to the 1 equals 3. Since 2 is less than 3, h of 1 is less than or equal to, let's say less than or equal to here. H of 1 is less than or equal to 3 to the 1. Then we could do the same thing for the last case, n equals 2. And I'll say note h of 2 equals 3 by definition. Further, 3 squared equals 9. Since h of 2, 3, is less than 3 squared, which equals 9, h of 2 is less than or equal to 3 squared. So we just prove that the base case holds for, or we just prove that the claim is true for all these base cases. So I'll say hence the base case holds. Make sense? Normally I'd write this into the base case holds, by the way, below, but just say to save some space on this very limited space whiteboard. I'm going to do that to the side. Anyway, though, let's do our inductive step. So the inductive step, remember, is how you prove, well, I'll show you what we want to show. So the inductive step, here we want to show that for all n greater than or equal to 2, we say, because that's when our argument's going to work, as we argued, for all n greater than or equal to 2, p of 0, we start at 0, and p of 1 all the way out to p of n will imply p of n plus 1. So the idea being, the inductive step, we want to show that everything up to n holds, we know the next case will hold. And then you know, that means the next case will hold, 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 chain reaction. So we want to show, in this case, i.e., want to show that for all, we want to show that, for all n greater than or equal to 2, if h of k is less than or equal to 3 to the k, for all k such that 0 less than or equal to k less than or equal to n, then h of n plus 1 less than or equal to 3 to the n plus 1. This is just writing out exactly what this is saying. It's saying that for all n greater than or equal to 2, we want to show that if it holds for everything between 0 and n, everything up to n, then it'll hold for h of n plus 1. H of n plus 1 will be less than or equal to 3 to the n plus 1. This is the big idea we want to show. So let's just do it. So remember, to do this is a universal conditional statement we're proving in this inductive step. So to do this, we're going to want to, I don't like this. This is like 2 periods. It's actually just a smudge, but you know what? We'll pretend it's the period. I feel better now. Anyway, so let's go ahead and let n be any arbitrary / particular integer such that specifically n is bigger or equal to 2, because that's when our inductive step takes over. Now, we want to show that h of n plus 1, oh, I'm sorry, I'm getting ahead of myself. Now, for every n greater than or equal to 2, we want to show that if the claim holds up to n, it'll hold for n plus 1. So here's when we make what's called the inductive assumption. So assume that for all n, or sorry, that for all k and z such that 0 less than equal to k less than equal to n, we want the claim to be true. We want hk to be less than or equal to 3. Okay, there we go. Sorry, got distracted. So we'll assume that the claim holds for everything up to n, everything between 0 and n. And this right here, this is what we call the inductive assumption. Assuming the claim holds for everything up to n is called the inductive assumption, or, depending on where you are in the country, the inductive hypothesis. It actually might not be a country thing. It's probably not slang. It's probably a department-to-department thing, or maybe even a person-to-person thing. This is your personal choice. Inductive assumption, hypothesis, whatever you want. But if someone mentions an inductive something like this, you know what they're talking about. It's this thing that we assume. All right. So this is the big thing we assume. We want to show that h of n plus 1 is less than or equal to 3 to the n plus 1. That's the big idea. So let's just get cracking, right? The whole idea in our side that we learned that like a long time ago, that we were using trying to prove this, the whole thing was that we want to write h of n plus 1 in this form right here. And then we can start dealing with the previous cases and everything will work out. But remember, this only holds as long as the index is bigger than or equal to 3. So first we need to show that n plus 1, that index, is going to be bigger than or equal to 3. And then we can use that, we can use the recursive formula on h of n plus 1. Otherwise, we don't know we can use it. So what I'm going to say is note, since n is greater than or equal to 2, n plus 1 is greater than or equal to 3, by adding 1, that's not 1, it's a triangle, 1 to both sides. All right. So now that we know that n plus 1 is bigger than or equal to 3, we can use the recursive formula on it. Thus, by definition of the H sequence, h of n plus 1 is going to be the sum of the 3 previous terms. So it's going to be h of n plus h of n minus 1 plus h of n minus 2. And notice, by the way, this didn't accidentally happen that n plus 1 is greater than or equal to 3. We specifically chose our n to be bigger than or equal to 2, so we added 1, we get to be bigger than 3, so we could do this. Like back when we were deciding how many base cases we needed, this is exactly what we did. We asked ourselves, well, what do we need to make n bigger than or equal to ensure n plus 1 is bigger than or equal to 3, so we can use this recursive formula. This is by design. Anyway, anywho, what do you want to say? Transition. We have this. And then remember in the aside, we were saying that, hey, as long as the claim holds from the 3 previous cases, this would be 3 to the n, this would be less than 3 to the n, 3 to the n minus 1, 3 to the n minus 2, and then we can go from there and prove this whole thing would be less than 3 to the n minus 1. That's the idea, at least. But in order to use that, in order to say that the claim holds for these, we need to make sure that n minus 1 and n minus 2 are actually in this range between 0 and n, because our inductive assumption just assumes that it works up to n. So even though it seems obvious, we have to prove that n minus 1, and n minus 2 are all in this range up to n. So what I'm going to say is note that since n is greater than or equal to 2, which is greater than or equal to 0, n is greater than or equal to 0, and since n is greater than or equal to 2, n minus 1 is greater than or equal to 1 by subtracting 1 from both sides, which is greater than or equal to 0, and since n is greater than or equal to 2, n minus 2 is greater than or equal to 0 by subtracting 2 from both sides. Thus, n is greater than or equal to 0, n minus 1 is greater than or equal to 0, and n minus 2 is equal to 0. So the point is they're all bigger than 0, which is good, because to be in our range where the inductive hypothesis holds, where we assume that the claim is true for everything up to n, we need these k values, these things right here, to be between 0 and n. So we know they're bigger than or equal to 0, which is good. Further, and once again, I'm going to go below the glare. Yeah. So further note, let's just get the whiteboard. So further note that n is less than or equal to n, n minus 1 is less than or equal to n, and n minus 2 less than or equal to n. That one's easy. It's really easy to show that n minus 1 and n minus 2 are less than or equal to n, that they're not up to n. It's a little harder to show that they're actually, that the lower bound thing works, but it's kind of obvious that it works anyway. But anyway, we need to prove it. So thus what this proves is thus, or I'll say hence, use thus too much already. Hence, we have that 0 is less than or equal to n, less than or equal to n, 0 is less than or equal to n minus 1, less than or equal to n, and 0 is less than or equal to n minus 2, less than or equal to n. Oh, nope, I meant to put it in here. There we go. That wouldn't make any sense. If 0 is less than or equal to something, if 0 is less than or equal to n minus 2 less than or equal to 0, that would mean n minus 2 equals 0, but a squeeze theorem. But anyway, actually that's not the squeeze theorem technically, but it's close. Anyway, the point is we've just shown that n minus 1 and n minus 2 are all in this range up to n, and we're assuming by our inductive assumption that everything up to n holds, and from that we want to show that n plus 1 holds. So that the claim will be true for n plus 1. So I'll say thus this time, by our inductive assumption, I'm really going to wear this word out today, by our inductive assumption, since these are all in the right ranges, h of n is less than or equal to 3 to the n, h to the n minus 1 is less than or equal to 3 to the n minus 1, h to the n minus 2 is less than or equal to 3 to the n minus 2. And here's where I normally say etc., but that's where we can stop, because that's all we care about. We just care about showing the 3 previous cases are less than or equal to 3, or less than or equal to their respective powers of 3, and they totally are under the assumption hold up to n, which is our assumption, which is how induction works. So if we put that together, then h of n plus 1, then we have that h of n plus 1 equals h of n plus h of n minus 1 plus h of n minus 2 by the above. And then h of n, well, that just equals what? Oh, h of n, I'm sorry, not equals. This is going to be less than 3 to the n plus 3 to the n minus 1 plus 3 to the n minus 2. We can say that because we just showed above that h of n is less than 3 to the n, h of n minus 1 is less than 3 to the n minus 1, h of n minus 2 is less than 3 to the n minus 2, and on like that. So we just showed this above. and I'll say since we showed h of n less than or equal to 3n, h of n minus 1 less than or equal to 3 to the n minus 1, and h to the n minus 2 less than or equal to 3 to the n minus 2. All right. So we know that h of n plus 1 is going to be less than 3 to the n plus 3 n minus 1 plus 3 n minus 2. And here's where the aside comes in. I believe it was Patrick in class who came up with this part. And that is, remember, that since n is bigger than n minus 1, 3 to the n is bigger than 3n minus 1. It's a bigger power of 3. Same thing with 3n minus 2. Therefore, this is 3 to the n less than or equal to 3 to the n plus 3 to the n plus 3 to the n. Because 3 to the n is equal to 3 to the n, 3 minus 1 is equal to 3 to the n, 3 minus 2 is equal to 3 to the n, on and on like that. And this is since 3 to the n minus 1 less than or equal to 3 to the n, and 3 minus 2 less than or equal to 3 to the n. We can also say 3 to the n is equal to 3 to the n, but it's kind of just copied it, so it's fine. But then what does this equal? Well, this equals, and actually I want to have these guys here. Just kind of showing how the flow of the argument works. What I wrote down is true. I just kind of like this better. It's like this equation leads to this inequality, leads to this inequality, leads to this following inequality. The following inequality is going to be that, well, 3 to the n plus 3 to the n plus 3 to the n, that is just 3 copies of 3 to the n. And what is 3 copies of 3 to the n but 3 to the n plus 1? Boom! Boom! That's totally how you do it, right? Oh, it's actually kind of perfect, so you can just see the inductive step right now in the proof. So what we, at the screen, so what we just showed right here is that if the claim is true up to, for all n greater than or equal to 2, if the claim is true for all things up to n, then it'll be true for n plus 1. So in particular, 2 is bigger than or equal to 2. And by our base case, right, the claim is true for everything up to 2. Therefore, by modus tollens, if you want to bring that back, the claim is true for 3. And then, since it's true for 0, 1, and 2, by the base case, it's true for 2 by the thing we just did, true for 3 by the thing we just did, it's true for everything up to 3. Therefore, by this argument, the claim is also true for 4. It's true for everything up to 4, so then it's also true for 5, 6, 7. This is the domino effect. This is the chain reaction. You just keep feeding this back into itself and just keeps popping out more and more and more and more and more and more and more answers, making our conclusion that is that for all n, I'll say therefore, for all n, and the set we were talking about want to be bigger than or equal to 0, that's what we had up here. So for all n in x and n, such that x is bigger than or equal to 0, h of n is equal to 3 n. Since we proved the inductive step and we proved the base case and the overlap there, that's everything you need to show the claim's always true. Done. And that wasn't that hard, I don't think, right? I mean, this was long. It took an entire whiteboard and a lot of desks. Oh, look at this for this little thing. But I thought it was worth it. I think really a lot of it's just structure, right? I mean, like proving every line here in the red is easy. The base case is really easy to prove. It's just verifying things. And in the beginning of this is just standard strong induction, right? Let n be any arbitrary integer such that n is greater than equal to 2, making sure that the base case overlaps here. Assume that the claim is true for everything up to n between the first case we care about and n. And then we want to show that it's true for n plus 1. And then here's where to start getting a little bit creative. But we've seen things like this before, where we kind of note the index and say, oh, okay, n plus 1 is this index, therefore we can use a certain recursive formula, and on like that. But this is where the creative part of a strong induction proof comes in. But I think you guys totally got this. So that's that. Imagine a pause right here. Actually, there'll be probably a literal pause if you guys are watching this. on the Canvas page. But anyway, if you're not, if you're watching this YouTube page, imagine a pause right here. So our next proof will acquire one assumption or fact. Fact. This whole proof, the whole conversation we're about to have is taking place in a McDonald's drive-thru. We're in a McDonald's drive-thru and thirsty for some chicken McNuggets. This particular McDonald's sells McNuggets by the 4-piece and the 5-piece only. So for some reason we go to the style, we want chicken nuggets. We gotta get the 4-piece or the 5-piece. We have to make some decisions. How is it gonna come to math? You'll see. Here's the claim. The claim is that there is some natural number n such that for all n and n such that n is bigger than or equal to n. So for everything bigger than n, we can purchase exactly n nuggets from a combo of 4 and 5 pieces. It's a weird claim. And then there's some number n, so for everything bigger than that, we can purchase exactly that many nuggets from a combo of 4 and 5 pieces for every number bigger than that. So for example, right, like, let's just start writing down some numbers here. 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll back those off. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Give myself some room here. There we go. That'll be enough. So for example, 2, we cannot possibly purchase exactly 2 nuggets when they only offer 4 pieces and 5 pieces, right? The smallest we can purchase is 4. So we can't purchase any 2 pieces. We also can't purchase any 3 pieces. Or you're also going to purchase exactly 3 nuggets. But we can't purchase exactly 4 nuggets because 4 just equals 4. So we just order 1 4-piece. And we can't purchase exactly 5 nuggets because 5 just equals 5. Just 1 5-piece, please. 6, well, we're going to an issue again, right? Because no matter how we combine a 4 and 5-piece, we cannot make exactly 6 nuggets. And same thing with 7. But 8, again, we can go, okay, wait, 8's 4 plus 4. So we can order 2 4-pieces and we'll get 8. So we can make exactly 8 nuggets. And we can make 9 too. 9's just 4 plus 5. How about 10? Easy, right? 10 just 5 plus 5. How about 11? We can't make 11. Right? No matter what we do, we cannot make 11. So this means that if there is a number n, just for all n bigger than n, we can make that number. That n's got to be bigger than 11, right? Because we can't make 11. What 12? Oh, well, 12, that's just 4 plus 4 plus 4, right? That's fine. Hey, 13 is one bigger than that, so that's just going to be 4 plus 4. Change one of those 4s to a 5, so we can make 13. 2 4-pieces and 5-piece. 14, oh, well, that's just one more, so we can change another one of those 4s to a 5. That's 4 plus 5 plus 5. And 15, just one more, change that last 4 to a 5. So we get 5 plus 5 plus 5. Now I claim that we already have everything we need to prove the claim holds for everything bigger than 12. What? How? It feels like we just scratched the surface. How do you know it's going to work for 17, 18, 19? How do you know it's going to work for 37? Here's the idea. Let's look at 16. Can we make 16? Sure, we can make 16. Right? 16 is 4 plus 4 plus 4 plus 4. 4 fours. Totally fine. But here's the real idea. Can we make 16 building off a previous combo? Because if you think about it, if we know we can make a certain number, well, then we know we can make that number plus 4, make that number plus 5 or something like that, right? Make the number plus 8. Well, 16, you could do 8 plus 8, for example. That's, we know we can make that because we know we can make 8, so we can make it twice, right? Just double that order. But still not exactly what I'm looking for. Instead, let's look at this. 16 is 12 plus 4. I like that a lot. We know we can make 12 because we just did it down here. Therefore, we can make 12 plus 4, just add an extra 4 piece to whatever this combination is. Not 17. Well, we could think of 17 as, for example, 9 plus 8. Once again, I think it's very useful. Instead, look at this. 17, that's just 13 plus 4. We know we can make 13. Just take whatever combo that is, add a 4 piece. Same with 18, that's going to be 14 plus 4. 19 is going to be 15 plus 4. 20 is going to be 16 plus 4. Do you see what's happening here? Once we've proven that it holds for 4 in a row, which we did from 12 to 15, we're guaranteed it'll work forever after that, because we can always just make the next number by taking the combo from 4 previous and adding a 4 piece to it. So 16, you go 4 previous to 12, add 4. 17, you go 4 previous to 13, add 4. And we know that we can do this with 16 through 19 because 12 through 14 was satisfied. But that means we can do it from 20 to 23 because 16 through 19 is satisfied. This is like the induction right here. 12 through 15, those are the first 2 cranks to get it going. But after that, we just keep referencing previous ones and keep filling in every single number. And we can show this for all numbers. This means that 1,300,112, we can make that with chicken nuggets. We know that to be a fact because of this right here. That's fascinating. And we're running out of time, so I'm just going to write out a very quick kind of proof sketch to show you how you do this. So our proof, there it is. Our proof is going to go like this. So we're going to prove by strong induction on n. Actually, first of all, right, technically I didn't say, I said there is some natural number n. So I'm going to say let n equal 12. Note 12 is a natural number. Because remember, in there exists proofs, you have to just verify. Yeah, 12 does fit the natural number mold. Now, proceed by proof by strong induction. Oh, I'm way off the screen. Proof by strong induction. All right. So here's how that goes. Remember, we always have our base cases, right? In our base cases, we want to show it holds. In our little thing we said we want to show it holds through 12 through 15. So once we get past 15, we can start proving it by referencing 4 back. But we can't do that until we get past 15. Because, for example, to reference 4 back from 15 was 11. And remember, we couldn't make it with 11. So this inductive argument doesn't start working until we have 4 previous ones. It doesn't start working until we get to 15. So that means we have to prove it for 12, 13, 14, and 15. So let's go ahead and let n equal 12. I guess I should say this is proof by strong induction on n. There we go. Let's go ahead and let n equal 12. Yeah. Note 12 equals 4 plus 4 plus 4. So we can make 12. I'm not being very formal here because we're out of time and all that, but we can make 12. That means that we can order it chicken McNuggets. We can make means we can do it. Let's go ahead and let n equal 13. Note 13 equals 4 plus 4 plus 5. So we can make 13. Let n equal 14. Note 14 equals 4 plus 5 plus 5. So we can make 14. Let's go ahead and let n equal to 15. Note 15 equals 5 plus 5 plus 5. So we can make 15. My 14 looks like an M. Weird. There we go. So this proves all of our base cases, right? 12 through 15, we're just verifying just through brute force that we can make them. That's totally fine. Let's do the inductive step. So the inductive step, remember, here's where we want to show that for all n, we want to go bigger than or equal to 15. Because we want to show everything up to 15, we can prove 16. Because we can subtract 4. We can prove 17. So you can go back 4. Just keep doing that over and over again. So I show that for all n bigger than 15, that P of 12 and P of 13 all the way out to P of 15, P of n will imply P of n plus 1. So once we get bigger than or equal to 15, the inductive argument starts working. We can say that everything up to n being true will prove that it is true. And notice, by the way, that even though we're only going to use the 4th back in our proof, we're not actually going to use any of the other previous cases, we still need strong induction rather than weak induction, because weak induction just says P of n implies P of n plus 1. But that's actually not enough for us. We don't know that P of n implies P of n plus 1. We know that if you go 4 back, P of n minus 3 or whatever will imply P of n plus 1. So we need to have all these in place. Anyway, in our particular case, what this is saying is i.e. for all n greater than or equal to 15, for all n bigger than 15, if we can make every k where 12 is less than or equal to k less than or equal to n, then we can make n plus 1. That's what we're trying to show, right? So, let's get down to business. Let's just go. Let n be any integer such that n is bigger than or equal to 15. Let's take a pause actually for a second. I think we take a pause. I feel like I'm going too fast. I took the time, I'm going too fast. Let's go. So we can make n plus 1. Let me be any integer such that n is greater than or equal to 15. Yeah. Now I want to show, now we have to make our inductive assumption, right? Assume, it's the inductive assumption, that for every integer k such that 12 is equal to k less equal to n, we can make k. So now we want to show want to show we can make n plus 1. That's the whole idea. If we can show that everything up to n implies we can make n plus 1, then we have the chain reaction effect will hold. And we can easily do this, right? Using this exact idea I was talking about, looking at the fourth previous and just adding 4. So let's go ahead and say consider n plus 1 minus 4. 4 less than n plus 1. Note that since n is greater than or equal to 15, n plus 1 is greater than or equal to 16. By adding 1 to both sides, I'm going to skip some steps here. Thus, n plus 1 minus 4 is greater than or equal to 12 by subtracting 4 from both sides. And that's incredibly important because, right, I'm going to start writing below the glare. That's incredibly important because we want n plus 1 minus 4 to be in our range where we can assume that we can make n plus 1 minus 4. We assume the claim holds true for this. So let's go ahead and note that 12 is less than n plus 1 minus 4, which is less than or equal to n, clearly because it's n minus 3 less than n. And move down here. So we know that this number, n plus 1 minus 4, is between 12 and n. So by our inductive assumption, assuming that everything holds from 12 to n, right, or up to n, or we start at 12 in this case, by our inductive assumption, I'm going to say hypothesis this time. Same thing. By our inductive hypothesis, actually, yeah, but by our inductive hypothesis, we can make n plus 1 minus 4, since 12 is less than or equal to n plus 1 minus 4 less than or equal to n. That's all we can do. You have to write that twice. We just wrote it. I just did it for posterity's sake. We can make n plus 1 minus 4. Thus, we can make n plus 1 minus 4 plus 4, right? Because we just add an extra 4-piece chicken McNugget. Keep your eye on the nuggets here, which equals n plus 1 minus 4 plus 4. Those cancel. This equals n plus 1. If we can do this, I'll say, it's not very formal, I'll say by adding a 4-piece to whatever combo made n plus 1 minus 4. We're so close. So now we can make n plus 1. Actually, this is exactly what I want to show. I want to show that if it holds up to n, we can make n plus 1, which we just showed we can. So that means we can move straight on to the conclusion. Which is, therefore, for all n in x in the natural and z such that x is bigger than or equal to 12, for all n in this range, we can make n. And just to bring it back, this wasn't there exists proof saying there existed this number n, big N. I'll say ergo, just to be fancy, n equals 12 works. Done. So there's the idea, people. This is proof by strong induction. I hope you enjoyed this one. I mean, how cool is this thing, right? This idea that we can show you can make any number, literally any number. Take 3.1415926 trillion, right? Take that number, you can make that out of nuggets. And you can prove that starting at 12 with this really simple form, right? All you do is you say it works from 12 to 15. And then this argument shows that as long as n is bigger than or equal to 15, and it works everything up to n, we can prove n plus 1. Well, 15 is bigger than or equal to 15, and everything works up to 15 from 12 to 15, so we can prove for 16. Then 16 is bigger than or equal to 15, so this argument tells us as long as everything works up to 15, which we showed it just did, then you can prove for 17. Or, 17. You can prove for 18. You can prove for 19, 20, 21, 22. This right here instantly proves our entire logic chain we're talking about for this chain reaction happens. We've proven that we can make every single nugget number, that's a nice, it's a nice mathematical term, up to or after 12, including 12. And look at the time. Actually, I gotta watch. Look at the time. I gotta go. So I hope you guys enjoyed this lecture. As always, if you have any questions. But other than that, enjoy your weekend off without discrete math homework. We'll be back at it next week, but really you only have like 3 homeworks left, 3 to 4, I think. It's kind of crazy how the year's coming to an end. But anyway, enjoy your weekend for now, and I'll see you guys later.